All right, hi everyone. Welcome to lecture 21. So, in this lecture, we'll be introducing the derivative, um, formally, uh, and this is kind of a nice, nice sort of turning point in the class because up until now, everything we've done has just been about, you know, functions and continuity and limits and all sorts of stuff like that. Um, and various notions of convergence and sort of working on our general analytic thinking abilities. But now we'll actually be able to introduce the concepts, the core concepts of calculus, and apply, you know, our 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 vastly more powerful framework for thinking about these things to these concepts from calculus. So I think this is where we really start to see the fruits of our labor so far in the class, if you will. So what's nice about the derivative is actually that the definition, given what we've done so far, the definition is very easy to state. So let me just give the definition, which I'm sure you've probably seen before, at least in a way that symbolically looks the same. So let f be a real valued function defined on an open interval containing A. So, of course, F could be defined at other places too, not just on this open interval. But the point is that it has to take value. It actually has to be defined on the open interval at least. Okay, some open interval. It could be a very small open interval, but some open interval containing A. Um, we say F is differentiable at A if the limit as x approaches A, f of x minus f of A over x minus A exists. Okay? So you'll notice that this is a two-sided limit, right? Which is why we need f to be defined on an open interval containing A. Right. So, for example, so like note that this means so technically this means a function with the domain equal to some closed interval is never considered differentiable at A or B. Okay, if the function was only defined on this closed interval, then it's actually not differentiable at A or B. Even if like the one-sided limit, right? Like there could be a well-defined one-sided limit of this difference quotient. This is called a difference quotient, by the way. I mean, just for some efficiency's sake to be able to refer to this expression, if we call this a difference quotient, then the one-sided limit of this difference quotient as you approach either the left endpoint from above or the right endpoint of this interval from below could exist, but that would still not mean that f was differentiable there according to this definition, because we need the two-sided limit to exist. Okay, so it's a little bit weird. I mean, I don't know. This is just the way the book does it, and that's what we're going to be using. So even if it seems like it should be differentiable there, we don't consider it to be differentiable there. unless it happens. So of course, if the domain of f contains more points outside of this closed interval, then of course it could be differentiable. But if the domain of f is just this closed interval, then, yeah, a and b are not in the domain of the derivative. So, right, this is different. That was differentiability at a point, right? Differentiable at a. So this is differentiability at a single point. And we write, so if f is differentiable at a, we write f prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. So, given f, we can define a new function f prime by f prime of a equals, well, this limit wherever it exists, then the domain of f prime is a subset of the domain of f, of course, right? So this is all just kind of like formalities. I mean, here it's like here you can kind of think of f prime of a as just like a single symbol, but here I'm really telling you that like f prime itself is a function in its own right, which just returns the value of this limit wherever that limit happens to exist, right? So of course, like just to, of course, I'm sure you've all seen it before, but the point of this definition is that these difference quotients, you can think of them geometrically as let me make a better, the slope, right, of, so let's say this is a, this is x, the slope of a secant line, so this is a line of slope f of x minus f of a over x minus a, right? So it's the slope of a secant line that connects the points on the graph of f where x is a and where x is this x, right? I mean, the points of the on the graph of f for these two input values, those points, you can connect them by what's called a secant line. So this is called a secant line. And this gives the slope of the secant line. And the limit is basically saying, like, if you let x get arbitrarily close to a and look at the slope of the secant line, if that approaches some number, then that's the number we want to be the derivative. And of course, if you look at this sort of visually and imagine this point approaching the other point, the secant line is going to get sort of like more and more, there's going to be sort of fewer and fewer points on the secant line between the two, the distance between these two intersections is going to go to zero, basically. So in the limit, if you look at a line whose slope was this, you'd end up with a tangent line, right? So f prime of a is the slope of the tangent line to the graph of f, at least under nice conditions. So what's very important for you guys to realize is that because we have made our definitions in such a broad and powerful way, this symbol has much richer meaning than what you might be used to from ordinary calculus. Okay, so this is from like, you know, basic calculus or something, right? You could call that like basic calculus, like an introduction to calculus for people who don't know analysis. This is kind of how you're taught to think about it. And it's not a bad way to think about it whenever you're dealing with a situation where the function you're looking at is, anything sensible, right? But the point is that this definition really can be applied to like any function, basically. Like any function, you can use this definition to tell whether it is or isn't differentiable. And many functions that are very strange looking will be differentiable at least at a single point, right? If you're looking at a single point, you can dream up some very strange exotic functions that are differentiable at that point. And the whole sort of tangent line concept kind of breaks down a little bit for those functions. Yeah, so let's just look at a couple examples. So some familiar examples. So like, for example, so let's just try, let's just do this one. So, so say f of x is x to the n for all x in R, where n is some positive integer. Okay. So then, so f of x minus f of a is x to the n minus a to the n. And there's a formula for this, which is actually related to the formula that you use in a geometric series, right? So like something like x to the n minus 1 equals x minus 1 times 1 plus x plus x to the n minus 1. That formula, you can generalize it to this very easily, because if you just factor out a to the n from this expression, then you get x to the n minus 1, or x over a to the n minus 1, and then you can like use this formula. But anyway, so this can be factorized quite nicely. So you get x minus a, x to the n minus 1, plus a x to the n minus 2, plus, and so in each term, the exponent of a increases by 1 and the exponent of the x decreases by 1. So then you end up with like a to the n minus 2x, and then like a to the n minus 1. Okay? So then, so for x not equal to a, for x not equal to a, the following formula is true. So we have f of x minus f of a over x minus a equals x to the n minus 1 plus a x to the n minus 2. Oh man, my tablet is acting strange. Plus a to the n minus 2 plus plus a to the n minus 2x plus a to the n minus 1. Okay? Okay, something, okay, hold on. Something strange is happening. Okay, anyway, sorry about that. So, so of course, at x equals a, right? At x equals precisely a, the expression on the left is not defined. But at every other value of x, these two expressions are equal. So we can take the limit as x approaches a on both sides to find f prime of a, right? equal, like the limit as x approaches a of this clearly exists, right? And it equals if you just, because I mean, this is just a continuous function for all values of x, right? So this limit, the limit as x approaches a here clearly exists, and you get a to the n minus 1 in every one of these terms, and there's n terms, right? So this equals n a to the n minus 1, right? So the fact that the two-sided limit of this expression exists tells us that the two-sided limit of this expression exists, okay? So there's a subtle like flow of logic here, but it's the fact that this expression is equal to this one for every value of x except for a, that, and then we can use this expression since the two-sided limit exists, and this is equal at all the values of x not equal to a, that means that the two-sided limit of the difference quotient exists. And so then we can use the, then we can take the limit on both sides, and we can use this expression on the right side to compute the value, right? And so the value we get is n a to the n minus 1. A was arbitrary. So, you know, f prime of x equals nx to the n minus 1 for all x in R. You know, that would be, you could write that, right? Because what we did was really just compute the derivative at a point, but that point was arbitrary. So we can like apply this formula to every point basically, right? So I want you to get in the habit of really thinking about differentiation as something that happens in a point by point kind of way. So like you can take the derivative at one point, you can take the derivative at another point. People get like, from learning calculus, people get really like calculus, you know, in a like in a sort of lower division context or in high school or whatever, wherever you might have learned calculus, it's easy to get really locked into an idea of differentiation as being some sort of symbolic operation where it's just like, oh, you know, just apply some rules like, you know, the product rule or the chain rule or whatever, and just, you know, do stuff to the x's. So like x to the n just becomes nx to the n minus 1 when you take the derivative, right? And that's fine for most functions, but the true meaning of the derivative is that it's just a number that you assign to a value on, like a value on the x-axis, a value in the domain of f, okay? It's just a number. That's the derivative at a point. And then you can get a function, which is the derivative at like all the different points, okay? So you really have to like think about differentiation as something that can or cannot happen at a given point, and that if you have a function defined at many points, you can ask the question of like whether its derivative exists at all those points and what the values might be. But it's not just, you don't want to just like willy-nilly just do these like symbolic, you know, pushing symbols around and doing algebra and stuff, okay? You really should think about it more concretely. Okay, anyway, I think that's going to be all for this video. And in the next one, we'll prove a basic theorem about differentiability and continuity.